I am using an iPad, so I only see 9 of you at any one time. So statistics may mean
Oh,
that may come into play here. So um, I was telling Dr. Mattingly earlier that I wrote out a list of what I'd like to talk about, and it's beyond what I could possibly fit. I'm going to use a timer on my wrist to cut myself off and switch subjects and general themes. And but I hope to pick up questions along the way. Normally, I enjoy working face to face with people. And so I'm used to people just being able to jump in and ask questions. That's a little more difficult with Zoom. So I'm aware of that. I will try to pause every little bit and see what questions might have come up. So as it's been said before, I'm Edward Case, and I did graduate from Andrews University with a degree in physics. And from there, I went into what's called radiation safety. And this may be a field that is unfamiliar to you, or sounds vague, and the field of radiation safety and health physics were actually new to me too when I was after I had graduated. And like today's COVID world, I also graduated in a recession. And so that when a job popped up, I did go away from grad school into health physics. And I started out in Loma Linda University Medical Center, where I got to work with the first of the large proton accelerators. They were still completing that unit when I arrived there. And so I was doing shielding testing of that unit, which was a 250 MeV synchrotron. And if we have some time, maybe I'll chat a bit more about that there. But I also got involved in dealing with research in nuclear medicine. And this really goes to the core of what radiation safety is. It's a support field to facilitate work with radioactive material and radiation producing devices, because they are useful phenomena, but they are also potentially detrimental phenomena. And so they need staff like us to be able to help those functions along, so that in the words of the Health Physics Society, to assist with the peaceful use of the atom. That was coined back in, I believe, 1948 or so, maybe 1950. From Loma Linda, I moved on, basically taking a promotion by changing jobs to the University of Cincinnati and Cincinnati Children's Medical Center, where I was involved in supporting a lot of research again, but also with radiation oncology and medical physics. I was assisting there. And in Cincinnati Children's Hospital with some experimental therapies that were being conducted there. They also had a subcritical pile and an underwater irradiator at the University of Cincinnati. And I was there for about 12 years. So I was 7 years at Loma Linda, 12 years in University of Cincinnati, and then I moved up over to University of Maryland. And that's where I am now, where I'm a senior health physicist here, and I assist with, again, there's research mostly in biology. Most of the research you see for what's called unsealed radioactive material is in the field of biology, where they label molecules or proteins to track their paths during metabolism. Or any other functions, for example. There's one researcher who does research with hemoglobin, and so he uses iron 59, and labels hemoglobin to track its movement in his experiments. Also, we have a research reactor here at the University of Maryland, which is we're still quite proud of it, and we do train operators there. And we have a large irradiator and a linear accelerator as well. So there's plenty to keep us busy here. That's what I've been doing for the last 27 years, is touching on all of these. What it was, though, when I graduated, was that a lot of this stuff was novel to me. So now that I'm going to talk to you about the field itself and some of the problems and issues that face us, some of the challenges because of real world incidents, I had to learn on the job. because in graduating with physics prepared me to understand the phenomena in a way deeper than many people in my field. However, there are no hands-on training for this field except for very few programs across the country. There's Colorado State, there's Bloomberg in Pennsylvania. And so health physics is pretty limited, but a physics degree prepared me very well for it. So with that introduction, let's talk about what is radiation safety. And well, the first thing you have to ask is, what is radiation? And radiation is energy that doesn't need a medium to propagate. And so the entire electromagnetic spectrum is covered by that. Or high energy particles that behave like waves. And we're not going to get into de Broglie waves or anything like that, I promise, especially for the math majors and data scientists and others. We're going to try to keep this on a pretty broad level. So that said, we're interested in radiation safety with a particular level of radiation called ionizing radiation. And anyone can just jump in if they have their mics open. What is ionization? And I'll listen for a voice, because it shouldn't just be me. Who can define ionization? Anyone at all?
Oops. When you remove a charged particle from an atom.
Correct. So you would have radiation of sufficient energy to remove an atom, remove an electron from an atom. And yes, like that was a nice, cute comment. Oops, I lost an electron, and that's very good. So what happens with this level of radiation is that you create perhaps more reactive substances, more reactive chemicals, but there are a lot of other things. It's just we're concerned about the energy. That was cute. I should be more positive. Anyway, I am going to go with the whiteboard here. So if I have incident radiation here, a chart, and I have an atom, when there's an interaction here, I'm left with an electron, and then that makes this a positive ion. That's all ionizing radiation is. The radiation was discovered in the late 19th century. Wilhelm Röntgen discovered ionizing radiation with they call the radiation X-rays. And the unfortunate truth is that the scientists of the time were not aware of what ionizing radiation could do to biological systems. For example, Thomas Edison was into ionizing radiation for a little bit, and he had he was happy to use his assistant and his hand for repeated experiments with the X-rays and for imaging, until eventually his assistant lost his hand due to accumulated damage to his tissues, and that's when Edison quit and became deathly afraid of radiation. And you're familiar, I'm sure, with Marie Curie and Pierre Curie, their experiments with eventually became known as radium, and Marie's unfortunate death from accumulated exposure to radioactive material basically she died essentially of radiation sickness over time. And that's because these things were learned the hard way. Radiation safety emerged because people learned things the hard way. The person who invented dosimetry film died 6 months after he invented it, because he was getting the feeling that, maybe I shouldn't be exposed to this. And it wasn't until essentially the Manhattan Project that health physics actually emerged as a field itself. They had safety protocols in place from the 1920s on, and it governed work at the University of Chicago, but it wasn't until Ernest Wolin, a physicist from the University of Chicago, created the field of health physics because of the demands and the fears around the Manhattan Project. And I will not digress there because I was going to talk about the criticality incident there, but I know there's other things to talk about. The Atomic Energy Commission emerged in the wake of the arms race as the Soviet Union and the United States engaged in a Cold War and designing all sorts of different weapons and missiles and stuff. And back then, even though we knew more about the health risks, and after Hiroshima and Nagasaki, the potential devastating effects of nuclear weapons and radiation and radioactivity, every single armed agency wanted their own atomic or nuclear weapons of some type or another. So the Air Force got nuclear-tipped air-to-air missiles to take out entire squadrons. No, they were never used. The US Army got bazookas that were nuclear-tipped and were absolutely impractical because it would have basically killed the person who fired the weapon because it didn't have a sufficient range to be safely fired. But they were all interested in it. So a lot of, for lack of a better term, cowboy research took place in the 1950s and 1960s. And that's why if you look back at some of the movies and 1950s, there was a lot of fear around radiation, a lot of radiation-produced monsters and things. And they make for very entertaining films, but very bad physics. The NRC emerged in the 1970s as a more closely, there was a desire to be more closely guarded and more closely regulated use of radioactive material and radiation producing devices happened. And since then, the regulations have become more and more robust. And in the wake of 9/11, security issues became paramount. And I have attended symposia with Homeland Security. I've worked with Homeland Security personnel. I've worked with National Guard in exercises, simulating dirty bombs or stolen sources. And I've engaged in training of SWAT teams and other responses for these very types of nightmare scenarios that were dreamed up, especially after 9/11. And that there's a fine line between caution and paranoia, and sometimes it seems like we tip one way or the other, with each potential incident. Anyway, so since then, since the NRC especially, there's been more and more work in the fields of medicine. Medical physics emerged as a field, and there have been some really great things that have come out. And I'll give one example, and that is the use of that experimental therapy at Children's Hospital in Cincinnati, which is called MIBG. The acronym is well, I just said the acronym MIBG, but I do not have the whiteboard space to write out the actual molecule. It's like methyl iodo. It's too long, but the use of it is that it's an engineered molecule labeled, what's called labeled, which is bonded to radioactive iodine, in this case iodine-131, which gives energetically too large what are called beta particles off. We'll get more into that part of things in a couple of minutes, because this is just telling you general intro. That molecule was designed to bind only to receptors on cancer cells, in this case, neuroblastoma cells. Neuroblastoma is a death sentence for children and is extraordinarily painful. It's cancer of the nerves, one can imagine. And when I was at the University of Cincinnati, I did train parents to be caretakers because the dose rate from this therapy was so high that nurses would not be allowed to consistently be the ones to directly take care of the children. Otherwise, with repeated children, they could exceed their limit, what their occupational limits could be. But what we saw is when this therapy was used, you would see when they imaged the child after the initial infusion of the molecule, all of the tumors light up on their body, and then in a few days, significant remission. And it allowed them to get off the heavy pain medicines that they were on. We're talking 2 or 3-year-olds on Demerol, and that not being quite enough. And I'll tell you what, there is no one tougher in this world than a kid with cancer. There is nobody that tough. And so I have found this field in my work and in studying its history extraordinarily rewarding. It's not the typical path that a physicist might take, but it has been one that I found valuable. So with that, now I'll pause for any particular questions. It's going to be time for some nuts and bolts after, if there aren't any questions. Dana, have there been questions posted? Okay, so let's talk some practicality. We're going to talk about some radiation units, and we're going to start with something called the Röntgen. And that is named for Wilhelm Röntgen, and it defines, let me take one step back. Let me take one step back from that. I want to measure ionizing radiation. What would be your idea of how to measure such a phenomena? We know what ionization is, so how would I measure radiation? Any guesses at all? None? How about, what if I have an ion pair? I have an ion, and I have a free electron. What are free electrons? If I have a number of them. Anyone can jump in. If not, I'll keep going. It's electric charge. So therefore, if I have a given volume, I can measure, and I can measure the electric charge within a given volume. I can back calculate, essentially, radiation. And that is what the Röntgen measures. It measures what is called exposure. Exposure is literally charge per unit volume, measuring coulombs per kilogram. And that is a large unit. The Röntgen is a large unit. I believe it's 1 coulomb per kilogram. I barely have to use it. Except as a understanding of incident radiation. So whenever you hear exposure used in this field, that is all it's talking about. And it's basically meaningless when it comes to phenomena with human tissue. This is only measuring how much incident ionizing radiation I have, and within a given volume or solid angle, if you want to define it that way. That's the first one. So that tells us, well, I know how much radiation I have. What I'm interested in, though, is what it does to matter. And so I have a second unit, actually a pair, and that is it's the rad and the gray. And what they measure is the transfer of energy per unit mass of matter, or in the case, human tissue can count as well, but there is a little bit of something that I'm going to add on. And the rad is the old school, unit, and it's 100 ergs of energy per gram. The gray is the SI unit used internationally, and it's 1 joule of energy per kilogram. This is a lot of energy. That's a lot of energy being absorbed. And so you're not going to see grays, being received by someone without it being, LD50 at least, if not just outright fatal. 100 ergs per gram is not very intuitive, but it's closer to real world numbers. By the way, we're the United States, so guess which one unit we use more often? If you say rad, you're right. We are stubbornly stuck on these things. So anyway, that's energy transfer. Okay, now I'm going to go on to one more unit that we're interested in. That energy transfer, again, it's called dose. So when there's a difference between exposure and dose, just so you know. The third one is dose equivalent. All right. We might as well call it this, the American version, it's the REM. And then we have the SI unit, which is called the Sievert. It was named after Rolf Sievert. And by the way, for most phenomena, the REM is equal to the rad, and the Sievert is equal to the gray. Their only difference is what type of radiation is incident upon it. And I haven't defined those yet, but there's something called the quality factor. Where it's, which is a unitless factor multiplied by the dose to give us the tissue effect. So in other words, it's a fudge factor. But you're going to find that there's a lot of fudge factors in this field. It's reflective of the fact that even after over a century, we still don't understand the field quite well. So for beta and gamma, the quality factor is 1. For alpha radiation, I messed up my alpha, its quality factor is 20. So it's 20 times. Now there's something very interesting about alpha though. Alphas don't travel very far in free space. They get absorbed very quickly, even for very high energies. But that becomes a big factor later. So I have some plutonium right here, literal plutonium. It's this source right here. And this is why I'm set up this way, so I can do stuff like this, which we will, demonstrate. I have here an alpha meter. And this is an alpha, what's called an alpha scintillator. And so, well, that's not quite close enough. I might have to remove it from that protective case right here. That's a bit better. So, but as I move this probe, it's dropped off to nothing. Just the air alone is sufficient to absorb this alpha particle. Now, why would that be? And if you don't know what an alpha particle is, it's a helium nuclei. And so 2 protons, 2 neutrons, very massive, is often very energetic as a result, because it takes a lot to overcome the binding energy of that. But it has a double charge. And we know anything about the subatomic interactions that, with all the fields, the magnetic fields that are generated by all the other atoms in and around that space, that double charge is going to mean that its path will be deflected, and very quickly. And therefore it's absorbed quite quickly. Now, where does that come into real life? Well, from an outside point of view, I can handle this plutonium source. But if you notice, I handled it from the edges. Because of the fact that alphas don't go very quickly, this is not coated with anything. It's literally just, it just has pure plutonium just sort of spat on there when it was created. If I actually touch the source, I could potentially pick up this plutonium on my fingers and stuff, and then eventually possibly eat it or something like that. And that's where alphas become dangerous, because now, whereas I had no hazard outside my body, now that I've taken it in, I'm bearing the full brunt of every single emission. Therefore, this quality factor of 20. This is also how, if you, I don't know if some of you might be too young to remember this, but there was a ex-Soviet, ex-Russian, I should say, dissident who was assassinated with polonium-210. And polonium's an alpha emitter. And it's, this material, it doesn't take much. It was a microgram of polonium-210 in a cup of tea. And that was enough to give him a lethal radiation sickness. And he died several weeks later. It's radiation sickness is not a fun way to go. And that is because of that alpha emitter. It does a lot of damage. The other type of radiation we could talk about is neutron. You only see that in fissile materials or with certain nuclear interactions, perhaps with accelerators, and it's completely energy dependent. How long ago was that incident with Livitenko? I believe it was about 2005, something like that, in that ballpark. And neutrons, they can be anywhere 5 to 20, depending on their energy. The energy dependence is there. So, any questions on these early units? Oh, do I exclude RF energy? Okay, well, that could lead to something here. Let's review something. I only have, boy, this is truly old school, but I don't like PowerPoint. So the electromagnetic spectrum. So this is showing everything from, what you'd get from power lines through radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Now here at UV, you start getting the photoelectric effect for certain interactions, but it's not counted as ionizing radiation. Only at this point on. And that's because, how do I calculate the energy of light? Anyone of the physics majors, come on, you can give me the formula for the energy of light, of a photon. Can anyone shout it out for me? Because my time's running. My time's running here. I can't. Anyone want to say?
Energy is Planck's constant times the frequency.
Exactly. So it is proportional to the frequency of the light, and therefore, the higher the frequency, the more energy I'm carrying. Back up here, if I bring up my sign again, we are in the radio waves and RF range. We are 10. We're in the megahertz range. Let's say kilohertz to megahertz range, 10 to the 6th, 10 to the 7th. But if you go up to X-rays, you're at 10 to the 18th. You are many, many orders of magnitude higher of energy by the time you get to ionizing radiation. In other words, RF radiation is of insufficient energy to cause ionization or to cause any sort of matter interaction of that type. There was a time, especially in the late 90s and early 2000s, where there was a lot of concern of signals from power lines or from cell towers, which now you get all sorts of conspiracy theories about 5G radiation, which is essentially the same as your microwave in that ballpark. And no, none of those things can interact the same way ionizing radiation can. They do not have the physical energy capable of doing damage to tissue. Now, a microwave could cook you if you had enough. If you had enough Webers on you, which means some of those yo-yos who may have climbed cell towers in the past to, for whatever kicks they might have had, and this has happened, have managed to sterilize themselves if they got close enough to the emitter for those big towers. And you will see warning signs where for RF, because and RF is measured in basically flux. It's a flux energy per unit area, and that's in Webers. And if it exceeds a certain threshold, you'll see these warning signs saying, "Hey, you're getting into an area where it's elevated." Or if you see a red sign, it's like it's potentially hazardous. But it doesn't interact with tissue the same way ionizing radiation does. So I talked about radiation absorption. Oh, I should talk about activity. See, here's the other thing. So we are not measuring things in typical fashions the way the other sciences do, and so when it comes to radioactive material, my typical physical measurements like volume, mass, they're not going to work. They're not going to tell me what I'm interested in. What I'm interested in is how much potential radiation am I getting from a particular substance. And so we have a unit called activity, which measures disintegrations per second. Well, what's a disintegration? Well, we haven't even talked about radioactive decay yet. You see, I knew I was going to run out of time here because I can't cover everything here. Radioactive decay, well, how many steps back do I have to go? Let me define activity first. Each disintegration per second, just consider it an interaction per second. This is a bit of energy or a charged particle that is being given off. And so we have two units again, the SI and the old school and American one. We have the old version is a Curie, which is 37 billion decays per second. And it's like 3.7 10 to the 12th, I believe. Do I have that right? I'm speeding through here. And becquerel is the SI unit, which is BQ for short, and it's 1 decay per second, 1 disintegration per second. So guess what? That's too big, that's too small. This is still popular in the United States. This is used everywhere else. There, that's what you need to know about activity. Well, now we have to step back and define things. Okay. Well, I have, what causes radioactivity? Well, I have stable and unstable isotopes. I don't know if any of you have ever seen this. This is called the chart of the nuclides. If you open up this chart, you have basically an outline, and this is going to be very hard to see, but it would be very hard to see in PowerPoint as well. But you're going to see each of these rows is for a different element, and the gray areas, which if you had it projected for very long, or like a map, the gray areas are stable isotopes. And if you go to the right, you are getting excesses of neutrons. If you go to the left, you have deficiencies of neutrons. And those elements that have excess neutrons or deficiencies are called isotopes. Same atomic number, different atomic weight. You also have things called isotones, which have the same. Isobars have the same atomic mass across, and they may or may not be. They wouldn't be the same element because you have this basically the number of neutrons change. And then isotones have the same number of protons. Now I don't remember because I never use isotones. I only use isotopes and isobars because that if I had the time, it would take an hour just to show you how to use that chart. I promise you. But it's very interesting. You should, if anyone is interested, get a chart of the nuclides, and you can trace nuclear interactions by just going up diagonals, for example, if it's a beta emission, or down diagonals for alphas, because they represent the loss or gain of protons, with these interactions. And I will show you how that works. That I promise. So we have stable isotopes, which are in that gray zone in the chart of the nuclides, and we have unstable ones. And unstable ones typically are those with excesses of neutrons. Why is this? Well, we have a line of stability. If I have a number of protons versus no, let's make this neutrons. Make neutrons and this protons. And I keep track of all the different elements that I have. Well, the line of stability is when it's 1-to-1. Beyond a certain mass, and this is because, if you wonder, how does a nucleus actually hold together? You have all those protons and you have these neutrally charged neutrons. why doesn't it fly apart? Well, that's where the strong force and the binding energy comes into place. And so as long as that's balanced out, those are stable. However, this line of stability starts to drift and goes toward a ratio of 1.5. That's what it takes to hold these. This is where these stable isotopes remain. And then beyond a certain point, they are no longer stable. The interactions between nucleons are insufficient to hold that nuclide together. It is going to be unstable. And how can I illustrate this? Well, okay, let's say you're going shopping. Actually, not online shopping, but actually physically going to a store. And I've done this. I've basically said, I only need one item in the supermarket, and I go in, and then I leave with 10, and I did not get a cart or a basket. So I'm doing this thing. I am unstable. And the only way I can find stability is if I eject some of that mass or find a better balance. And the way that's done is I have to get closer to that line of stability. I have to get, if it's a very large nucleon, I want to get rid of as much mass as possible. So something like uranium-238 is going to get rid of an alpha particle. That's 2 protons, 2 neutrons. That's the most it can get rid of at one time. And then it's going to be thorium-234 because I got 2 protons down the periodic table. And if it's something that isn't so massive, but I have an excess of neutrons, then I have something like this. So let's say carbon-14. Carbon-12 is your stable isotope. Well, what happens to carbon-14? Well, carbon-14 has 2 extra neutrons. It wants to find stability. Well, it doesn't need to get rid of so much mass. So what it does is very interesting. It emits what's called a beta particle. And a beta particle is equivalent to an electron. At least a beta, I'm not going to go into the positron decay yet. So if it's an electron, where did that electron come from? If it's from the nucleus, what do you think happened? Does someone want to jump in, or shall I keep going? Okay, I will answer that. It actually comes from a neutron. And if I take a negative charge from a neutral particle, that becomes a positive particle. Therefore, what I've done is that I've moved up the periodic table. See, I have my atomic number 6 here for my carbon. But if I changed this mass stays the same, but I changed a neutron to a proton, suddenly I've become nitrogen-14. 7. That's a perfectly stable atom right there. And then I have something called the beta particle, beta minus, and there's something called an anti-neutrino too, but we don't have the time to get into the weeds there. And that's beta decay right there. It's all in the name of seeking stability. And is everyone good with that? Were there any questions so far? I've been pretty basic to cover the broad level of majors we have here. All right, very good. Very good. Now we can finally get into some of the other things. We can talk about binding energy. Now, what's my equation for matter and energy equivalence? Someone can answer that one.
E equals mc squared.
Very good. E equal mc squared. Thank you. Please feel free to jump in. I'm trying to, I'm not used to being a monologuist. Equal mc squared. However, I'm dealing with kilograms and my energies in joules, and so that's not going to really work for us. We need something else. So we need an energy unit that can deal with our field here. So we have the electron volt, the EV, and if you want to know what an EV is, it's the amount of potential energy that if, let's say I have a vacuum and I have 2 charge plates and I have a potential of 1 volt, and the amount of kinetic energy picked up by a single electron going from one charge plate to the other is 1 electron volt. That means it's a very small unit of energy, and what we typically deal with in ionizing radiation is in kilo to mega electron volt ranges. Okay, so that's the energy I'm interested in. So my mass, kilograms, is way too big. So what I need is something called an atomic mass unit. An atomic mass unit, well, is literally defined as 1/12 of carbon-12. That's the way it was defined. So let's, the 1 AMU equals 1/12 carbon-12. All right. This is where we're going to discover something very interesting. I have individual masses of my nucleons, let's say, and we have, for a proton, the mass is 1.007276, and the neutron is equal to 1.008. It's a little bit bigger. 665. That's right. I believe. So already, I'm seeing something. If I have 6 protons and 6 neutrons, which makes up my carbon nucleus, my mass is going to exceed that 12 AMU. Where did my extra mass go? What happened? Well, that mass gets converted to energy, E equal mc squared. And because I feel that I was going to run through this calculation, but you literally just add up your protons and neutrons, 12 of them, if you want to do this calculation. Take the, subtract 12 AMU from it, take the difference, and you can calculate the binding energy for the carbon nucleus, which turns out to be, well, if you go ahead and take it one step further, if you want to calculate the literal energy equivalent of 1 atomic mass unit, that's a 931.5. And then if you do this conversion right here, let's see, did I write that down, or because I don't want to take the time to do it for you because it's too many steps. I'll tell you what, the difference you get here is a term we call the mass defect. And for carbon, I believe you end up with something like 0.09894. So that's your fraction of atomic mass units. You plug that into your E equal mc squared, and you will have the energy, your binding energy, in electron volts. So, but I'm going to leave that alone for now because I know that I'm taking too long with all these concepts. Do we have any questions so far on that, or would you rather have me go into the more down to earth stuff? I just wanted to define a lot of these terms for you so I could actually talk about my interactions in the ground. Does anyone have a preference one way or another? Yes.
I'd like you to maybe look at the question or the comment from Mickey about what's a day in the life of the health physicist like.
Okay. All right. Yeah.
I think a lot of people would enjoy. I mean, we've had 57 people.
Wow.
And that are very interested in what you do for a living. And what's it like? What's the work like?
Okay. All right, well, let's get rid of the science for now. The direct equations. If we have time, I can do a shielding equation, but otherwise, let's talk about health physics itself. For that, well, I'm looking to protect everyday users of radioactive material and radiation producing devices, X-ray units, linear accelerators, that sort of thing. So I'm interested in those terms I defined earlier, their dose. We have what are called occupational limits for dose. For someone like myself, I have this dosimeter, and I can show you up close right here. This is a TLD. with a neutron absorber to measure my dose. And that's one of the things we do as health physicists, is that we track this absorbed dose for every, literally dose equivalent for every user of ionizing radiation. So we have one of our specialists, one of our health physicists, specializes in dosimetry alone, and they have to keep track of the doses of all these people. Well, what if they have a dose that, how do we know that a dose is high except if they exceed that big limit? Well, that's not exactly practical. We can't wait a whole year to exceed an annual limit. So we have a term called ALARA, and that stands for as low as reasonably achievable. And that means that we are charged with minimizing dose to occupational and members of the public too, but in a different way. Occupationally exposed people to radiation levels as low as reasonably achievable. Dosimetry is one way we do this, and we actually have levels which would trip, by definition, ALARA levels. One of the things that you probably should know as a health physicist is that all these calculations and stuff I was doing, well, that's just to show you, some of the science behind it. Really, it's a fusion. It's a hybrid field of science and law. And there are many, many regulations published by defined by the Code of Federal Regulations that have to be adhered to. And those limits are part of that code. Let's see. I'll answer that question in a bit. So just quickly, I'm allowed 5,000 millirem per year. That's my limit for for what's called my whole body, which is my torso. That's they care about the head too, but it's got a slightly different limit because there's a different limit for the eye. So it's my torso down to my knees, basically. That's the whole body. And that's because radiation applied to a whole body is much more detrimental than something to an individual organ and stuff. And I'm going to jettison that dose calculation I'm going to do too, because I think it's more interesting to do this nuts and bolts. So I'm limited to 5,000 millirem per year. Well, if someone is working with it and they exceed, let's say, they normally get almost undetectable radiation, but 1 month, one period of time, their dosimetry results end up something like 900 millirem. It's not enough to trip that annual limit, but it would get our attention, and we would conduct an investigation. We would look into what practices are they doing? What did they do during this period? Are they running their experiments in a way that that is potentially risky, for lack of a better term? And we would see if we would have to adjust practices and see if they are doing their due diligence, conducting contamination surveys and that like. That's one type of investigation that could be conducted. What else do we do? Well, thanks to DOT regulations, Department of Transportation regulations, you cannot order radioactive material directly to your house, let's say. You would need what is called a license, and you would also need a designated space on that license to receive radioactive material. And that is another job that we do. We have that designated space. We receive radioactive material so that the researchers can continue conducting. So we have someone else who normally handles those deliveries. I typically I specialize in the radiator, sometimes with the reactor, but I hop around in a lot of different spaces. With the irradiator that we have, I conduct water samples of an underwater irradiator. That underwater irradiator has cobalt-60, and we are very interested to see that the sources within that underwater irradiator remain intact. And so we take water samples, and I would run them on a high purity germanium counting system. And I look for the telltale signs of cobalt-60. Thank goodness, knock on wood, that has never happened. But that is required by regulation. These are just some of the examples of things that we do. I also work with radioactive waste and was involved in dealing with the legacy of all the cowboy research I talked about in the beginning. There were a lot of sources that probably should not have been possessed at one time on this campus, for example. Uranium hexafluoride gas, for example. I told Dr. Mattingly about this earlier this week. Uranium hexafluoride, because of the fluoride part of it, can erode the seals of gas cylinders, and those cylinders become explosive. And so it was in our best interest to get rid of this potential hazard. And the name of radioactive waste is minimization of risk. We want to get rid of sources that are no longer being utilized and get them to proper disposal channels. And that's so I was involved with shipments and things like that. I've been involved lately with being kind of a babysitter of a construction crew, because they were working within a lab that had radioactive material in it while they were installing a new HVAC system. And because of regulations, security regulations, which means that either sources have to be secured or maintained line of sight. And if it's an active lab, the potential contamination, you have to conduct surveys, which I did conduct a survey for contamination in that space. And you have to be there with these unauthorized personnel is what they are. And so I was doing that. Dana, you have a question? I know there was another question that popped up.
Yeah, there's a real interesting question. It goes to this safety issue you're talking about now. We used to do Crookes tube demonstrations in class, and then the state of Michigan said that wasn't safe. Do you agree it's not safe, or is this over-regulation?
The Crookes tubes, they generate X-rays, correct? And they are unshielded. And now X-ray devices require several, either certain practices that involve cordoning off, where, basically, for lack of a better version, sort of like procedure-based interlocks, if you have an open unit like that. Most everything since the days where those Crookes tubes were used more often have been involved in more self-contained cabinetry units, which have built-in interlocks and automatic shutters and stuff. Yeah. Yes.
So the analogy was made to X-rays that would be emitted from an old-fashioned TV screen. Would those have been considered confined in the way that you're talking about, or?
It's interesting you bring that up, because a typical CRT, for example, is an electron gun. And it fires 50 keV electrons toward a phosphor screen. This is why they used to tell kids in my day not to sit too close to the television set. You'll get X-rays. Well, it's partially absorbed by the glass and stuff. And it's like, well, why do you get X-rays? Well, that's because of a phenomenon called Bremsstrahlung, or braking radiation. If you decelerate a charged particle too much, too suddenly, by conservation of energy, it emits a photon. And when it involves free electrons, that is an X-ray. So the most that X-ray could be is 50 keV, but that is still technically ionizing radiation. So Crookes tubes, if they're in that ballpark in the 50 keV range, would technically be ionizing radiation. Not terribly energetic, Now it's not something that strikes fear in the hearts of health physicists, but it is ionizing radiation and would be treated as such. It's interesting. Michigan is not what's called an agreement state. Agreement states basically come up with a an agreement with the NRC and say, we can run our own program, we can run our own show, and then they do their own state-based regulations. So this is an NRC inspector that would have said this to you. Is that correct, Dana? Was that an NRC inspector that said this? Or
We
Nikki?
need to ask Professor Kutzner. He says
Oh,
that he
okay.
thought it was a state person.
Yeah, so, sorry, I'm the radiation safety officer at Andrews, so I'm gonna speak up just a little bit. It seems that the Michigan State is regulating X-ray devices and other radiation is
That's
through NRC.
correct. Yeah, you're right. You're right. It is state-based for that. I did take a little time this week to take a peek, and yes, the state of Michigan is, so probably their Department of Health is regulating X-ray devices, but but all materials is still under NRC. And so that's interesting. It seems that you should have been able to come up with a protocol that would have convinced the state of Michigan that you would still be able to do your Crookes tube experiments, but you would have to demonstrate that you would adhere to the ALARA principle, basically, that you would minimize potential dose force towards students and such with these experiments. But you probably have to come up with a detailed protocol and procedure and try to sell that to the state. And have you talked to Central Michigan University about what they do with Crookes tubes and stuff?
We haven't really pursued it. I hadn't
Okay.
actually thought about doing that. That's actually a good idea.
Yeah, I remember Central Michigan's people, they did some of that, and so it'd be worth approaching to see if they have either tabled it or if they came up with some sort of protocol. My guess is that somebody, certainly maybe at Ann Arbor, have come up with a way of being able to conduct that very basic experiment.
Yeah, I think Dr. Kutzner was talking more about demonstrations in the front of a classroom, but I think we can work with these people to figure something out. That might be a good idea to do.
Right, and you know, when it comes to demonstrations, that ALARA principle comes into play again, because there are three ways to maintain the people observing the experiment safe. You know, time, distance, and shielding. And you know, and I'm going to skip the shielding calculation because that's going to take too much time. You minimize the amount of time around the source. Demonstration is, how long are the typical demonstrations? I'm just going to use that as the example.
I never got to see the Crookes tube demonstration. 30 seconds, Kutzner said.
Yeah, so that sounds like the window of time is pretty good. Distance, because radiation follows the inverse square law. And if you want a quick demonstration of that, I have here some carbon-14. And I have here a Geiger-Mueller chamber. I don't know if I'll get a chance to define that, but it's pretty active. But as I increase my distance, and it's literally just off the screen where the source is. The inverse square law is very, very useful when it comes to the situation you're describing. So if you come up with a protocol that actually defines how far away the students might be, I would think that could be sold. But again, I would consult with Central Michigan, maybe University of Michigan people. The University of Michigan has an outstanding radiation safety program, so they should be able to help you and see why Michigan seems to be so conservative on that unit. You know,
I think they basically just have an issue with unshielded X-rays, as you said.
Right. But I would still think that University of Michigan still might have had some. Health Society would help as well. University of Michigan still had diffraction units that might have been outside of cabinets.
Okay.
You know, and
We'll definitely look into that. Thank you.
Yep. So anyway, like I said, I'm going to skip the calculations. We're going to keep talking more about the type of work the field itself involves. Some of the activities that we do involve, I mentioned when I was observing those construction workers, was a contamination survey. And that literally can be as simple as taking some scored material and wiping it on the surface and then measuring it in a number of different instruments. Now, I mentioned the high purity germanium instrument we have. We have a gamma counter, if that's the type of emitter that I'm looking for. We have what's called a liquid scintillation counter. And what is liquid scintillation? Well, that's talk in itself, but let's just say I am taking a radioactive sample and literally surrounding it with a liquid-based scintillator. The way we measure radiation at all, I told you how we measure, the Röntgen, we measure ionization. This GM instrument right here, this little chamber, which actually I have an open one. I put a large charge across that chamber. I thought I had a version of that open with a pop chamber so you could see. It's just a filament across a charged space, and I measure the amount of electrons coming onto that filament. Because of that potential I've applied across that chamber causes the electrons to drift to that filament. There's another type of instrument called a scintillator, and that's this type of probe right here, and it has a crystal. And the principle that we're looking for is that we're either looking to generate electric pulses, or we generate light toward through the photoelectric effect, eventually generate an electric pulse. So we have a way of counting things. And there's a crystal right here that with incident photon-based radiation, it will excite molecules within the crystal, and it'll drop to ground state and emit an electron on the other side. I saw a hand raised there for a second. Well, liquid scintillation does the same thing, except that my crystal is liquid. So for very low energy or for very small quantities of radioactive material, that comes in handy. And this is a photomultiplier tube right here. This is inside this probe. And so I accelerate the charge that might be picked up from generated from that photoelectric effect, and I amplify it. There are other types of counters called proportional counters and ion chambers, and they all are designed to measure different things. Ion chambers have the great capacity to be accurate because the number of ion pairs generated within its chamber equals the number of ion pairs detected. So that makes them extraordinarily accurate, unfortunately not very sensitive. While on that Geiger-Müller counter I showed earlier, that has a potential applied that is so high that when a single ion pair is generated, it causes an avalanche effect, which in electronics, it means that I've basically ionized my entire chamber. And that makes them very sensitive, but there's a dead time as that chamber resets and becomes stable again until the next detection causes the next avalanche. And so we use these type of detectors to detect contamination. Sometimes, like the ion chamber, they're great for dose rate. Sometimes you have hybrid type of detectors that you can use to do both, but they're more energy dependent. And so all these factors come into play. I have to know what I'm dealing with. Is it a device? Is it what kind? If it's material, what kind of material? What kind of emitters am I looking at here? Another thing that I do, I have helped researchers with their conduct their studies because of our instrumentation available. I've mentioned all those different counters we have. Well, they may not have the same equipment we have. So I have helped researchers from NASA, which the Goddard Space Flight Center is just a couple miles down the road from where I am right now. And I've had people, they have gear too, but I have better gear than we have, I'm sure. But they requested our help in conducting some studies for them. I have someone who has been doing ongoing work at the Trinity site in New Mexico and bringing these soil samples, and I do analysis for them, or even on campus. Some of the researchers have asked to use our counters, and recently I got a thank you in a paper that was published because I helped them conduct their analysis. You know, I mean, some of the things that you see you see some interesting things. You know, if it's an animal study, and I'm sorry for those who are squeamish. You know, mouse studies. Well, they have to eventually cut up those mice. And yes, Margarita.
Just as we're winding down, there's a question that I think would be very important for you to answer. This is Josiah's question. What courses best prepared you for health physics? You know, if you know they're getting ready for the spring semester, and the rest of the time they're going to be here. What courses, if they are interested in your line of work, what are the courses that helped you the most?
Nuclear physics, E&M, optics. Those three are the big three right there.
Well, we don't have nuclear, but we have particle physics, and so
particle physics.
We actually get into some nuclear there.
You don't teach nuclear anymore?
No.
I still have my crane.
I know. I teach it too, but it's there's not that much interest in the nuclear, and we can't teach it from fundamentals as well as particles. So I do a hybrid, particles with some nuclear.
I knew the time was going to get away from me, and I had a lot of stuff here, and I knew I made it too big for the time period I had. But to maintain with this theme, I was informed in the beginning that there's a biomedical physics program that's emerging there, and that also, if I had that available and I knew about health physics, that would be very important to get into. I would want, because everything that we do is in the interest of maintaining dose and human risk minimum. And the way we do that is by understanding how radiation interacts with human tissue. And so the biomedical physics already sounds like it would have been a great boon for me. Also, it sounds like if that's going to be expanded upon, that's something that can lead into an adjacent field called medical physics, which is a fusion of medicine and physics. And it is used for the design of therapies and doses. Radiation oncology, one particular type is called brachytherapy. And brachytherapy involves the surgical implantation of sealed sources in proximity to, say, solid tumors. That's sometimes they're temporary, sometimes they're permanent, but you know, you're dealing with radioactive material and the amount of dose that you could potentially get off of each and every one of these sources. Well, the medical physicist is going to design what the array of material is going to be in conjunction with the radiation oncologist, so that they can provide an accurate dose to in the array they want. And so that's a master's or PhD level field, and those that is a very helpful field. Radiation oncology is in constant need, and so medical physicists are in demand. There are not many health physicists now, and in fact, it's a graying field, largely because of the decline of use of nuclear energy since 3 Mile Island. There have been a number of mothballed nuclear plants since then. However, there still may be a return to that. One of the problems with nuclear energy was the waste issue. That's, again, another talk for another time. But now with the idea of smaller nuclear plants, and I know Bill Gates is one of the people who is financing this because it's green relatively, and so there may be a resurgence of health physics in that respect. For now, there are still programs, master's programs at Bloomberg and at CSU, Colorado State University, and that would that you can branch into once you have your physics degree. But that's a long answer to your question, which is what classes would be most helpful. The three I named, but I guess particle physics would be important, and also the biomedical one. So if anyone is interested in that field, that's where I would go. Are there more questions? Because I can keep talking, and I already know I hit the time. You know, I didn't even get to talk about the Gojana incident in Brazil, or the recent incident at the University of Washington, or even
Sounds
Chernobyl,
like
if you guys were out there.
we need story time sometime soon.
Yeah, probably. Yeah,
The
probably.
other thing I was thinking is that our students will be looking for clinical sites to visit. And I was thinking
Okay.
that you might be helpful there as we're finding places for our students to go to at the end of their biomedical physics degree work.
Well, most hospitals of, you know, most full-fledged hospitals, not clinics,
Right.
have nuclear medicine programs. And I believe if you contact them, you can arrange for tours and visits to the nuclear medicine departments. Radiation oncology is a bit more specialized, so I'm not sure which hospitals in the area, but you know, you're in the certainly close to Notre Dame, and
There's
so
actually a medical physics university in South Bend.
okay, so
Okay,
I was
from
figuring somewhere around there
Right.
that you could talk to them about that field,
Right.
and in general, they're still Cook Nuclear, and they
Yes.
still tour.
Not any. They don't let
They
you go all
don't?
the way in. I went in. I was one of the last. That
Really,
went
they
in
ended
all
the
way into
tours.
the reactor.
Oh, I am disappointed. I'm
No,
disappointed.
it's just not safe.
Uh,
They can't. It was shortly before 9/11, and
Oh, I see. For
closed
security
everything
reasons,
down.
I should have remembered that. I should have
Yeah,
remembered that.
it's
That's
not
true.
like it used to be.
No, it's
They
not.
still allow student groups, Margarita. You can work with them as a school to get a student group. The general public can't.
Yes, but you can't go into the real reactor. They
that's
have.
Oh, no,
they
no,
have
no.
a fake
Yeah,
one.
yeah. They would not allow you in the proximity of the reactor itself. But they certainly can be very informative. Now, there
Yeah.
are still training reactors. There's a number of them. We have one here at the University of Maryland, and Penn State has one. It's still a bit of a drive, but they have a great 1 megawatt reactor that they do tour people. If you did a really long field trip post-COVID, I do know the personnel at Penn State because they have a Penn State roundtable. They're great over there. And if there were enough people and you were really interested, I'm sure we could get something arranged.
Well, I know that Tiffany graduated from the Tiffany Summerscales, graduated from Penn State. She probably has some buddies that would connect us.
Yeah.
I did tour the reactor when I was a student.
Oh, you did?
Okay, there you go. And there's also Michigan. I believe University of Michigan might have one.
Well, that's closer.
Yeah, it's a lot closer, but I like Penn State's. So were there other questions, Dana? A little bit?
Well, that's been very.
I actually had one myself,
Okay.
which was, you talked about learning on the job and how you got a regular physics degree and then you went into this specialty. I had heard from other people that that's no longer possible. Is that true?
No,
you have to have a degree that's specific.
It depends on how low you want to start on the totem pole. Certainly, I see programs that hire technicians that really just want someone in the sciences, and sometimes they don't necessarily, you know, they usually name experience, but with someone in the field, they may make an exception, certainly. And when you're at the technician level, you do learn on the job as well. And they just want someone who could understand the concepts that they're going to be talking about. So So I've even seen a zoology major end up in the field. So I don't think that's not, you couldn't get in as an HP, as a health physicist. That would take a lot of experience built up from the technician on. And there's also certification programs that can be worked toward. But that's something, again, once you're in the field. And there are certificates you can seek, though, as well. And our RPT, for example, are being one of them. And so I would disagree with that. I think that you should be able to find something there. And by the way, speaking of circuitous paths, I also have a master's in history, and I do creative writing on the side. So I'm a very curious person, maybe even a bit of a dilettante, but I found that my broad-based education has assisted me, because it's not only the science that you need, but the ability to integrate it within a broad array of fields and be able to communicate effectively about it. I apologize that I got into the weeds so much in my talk. I know that there might have been more interesting things that I could have gone into, but I was starting out assuming that I didn't want to talk in jargon and lose everybody. So hopefully that was okay. That was enough of an indulgence.
Tell us